again. The only person besides the two I know aren't going to be here that I don't see is Colton. Colton, not here? Okay. We're going to talk about work and energy today. I'm going to talk just slightly more about the Coriolis effect just to make sure we have that down. One thing I want to make sure I mention, if you find a problem with something like the Concept Coach, so far I've had 2 people who have contacted me with problems with Concept Coach where the problem had a problem, right? One of them was where it asked for the angle going from 12, well, it said 12 p.m., but we all know there is no such thing as 12 p.m., so 12 noon to 3 p.m., and it had 2 angles for that one angle. Yes, sir. You guys didn't want to see that? Yeah, yes, you can wave to them. That's true. Okay, so that's what I thought you were seeing. The other one was a problem that asked you about comparing the final speed on different paths. And then it showed you a graph that showed position, the x-axis versus time. Only one position graph, you can't answer the question. They didn't. Looking at their description, it was supposed to have something with a spring, and it was supposed to be a completely different figure. So if there's problems like that, make sure you let me know so I can take care of things and not just I guess they lost points because of a bad question. Yeah.
Is it supposed to ask us questions about the coming section?
It's not supposed to. No. If they're out of the section, let me know because I want to let them know of those problems too. Because it's supposed to ask you like generally 2 questions from a past section and 3 from the current section is what it's supposed to do.
Yeah. There's a prompt to report errors, so what I did is I just put on and explained.
Yeah. So just want to make sure we're all on the same page there. People aren't like, I can't deal with this. All right, so looking at the Coriolis, this is slightly different, but basically the same slide we had last class period. Remember, the Coriolis effect, I said, was due to the rotation of the Earth. So I want to focus on this figure here because, when it's not zoomed out, it's kind of interesting. This is showing things about what happens on Earth because of the Coriolis effect. So let's start with something real basic. At the equator, it tends to be hot. And so because it's hot, the air expands. When it expands, it becomes less dense. That is, the molecules are farther away from each other, so the mass per unit volume is less. And because the hot air is less dense, it floats up. So you have a general behavior on the equator of air floating up away from the equator. But as air floats up from the equator, then that means that air that's down on the surface of the Earth has to go toward the equator so that it can replace the air that floated up. And so on the Earth, you're going to have the air doing what is shown here. So you're going to have air from north of the equator go toward the equator, but the direction of the surface of the Earth in the direction it's rotating, that is the eastward direction, that speed is fastest. Okay, I should use a different color to illustrate speed compared to the flow of air. So the speed of the surface of the Earth is fastest at the equator and, of course, 0 at the poles. So this air that is going toward the equator, as it gets closer to the equator, its speed toward the east is not as fast as the Earth's speed toward the east. And so that means that the air that is going toward the equator is going to curve to the west, as seen by Earth. And that's because the speed of the surface of the Earth is faster at the equator than it is when you go farther. So that would affect your wind directions if you are, on the Earth near the equator. Now that hot air that came up, as the air goes up, the air pressure decreases. Air pressure is simply the result of the weight of the air above you. So if you go higher, there's less air above you, the air pressure decreases. And you guys have probably already learned things like the ideal gas law that says if the pressure decreases, the volume is going to expand. And so it expands, but because it expanded, it also cools. Because it's cool, it can't hold as much water. So the rising air at the equator expands, cools, drops out its water. So you're going to have a lot of rain around there, right? I grew up in tropical areas, Liberia and Sierra Leone, and we just had rainy season and dry season, and it was because of these kinds of things. So then you have this dry, cold air. It came up at the equator. It's got to either go north or south. And so it goes north or south, depending on which side of the equator you're on. And it starts falling down and heating up. And now this air falls down, generally around 30 degrees north or south. And so now as it falls down, it's getting compressed, the temperature goes up, so you have a hot, dry air coming down. Hot, dry air coming down, there's no moisture there. What's that likely to make on the earth? A desert. So you have lots of deserts in this region. Okay, that was a bad idea. Where it says dry that I crossed out because, where it says dry, you tend to have deserts there because you have this hot, dry air falling down. Now, last thing I'm going to say about this. A few years ago, I flew to Asia with the honors trip, their poverty and wellness field trip, which is awesome. And one of the things that I hadn't really thought about was the time it takes to fly from here to Hong Kong is significantly different than the time it takes to fly from Hong Kong back to here. And the reason is, if we're going to fly from here to Hong Kong, we were going west. That is, we flew from here to Los Angeles, then from Los Angeles out to Hong Kong. But we're flying up in the upper atmosphere where the air is going this direction. So that air starts at the equator and is going away from the equator. What's happening to the airspeed compared to the land speed as you move away from the equator? Or maybe I should just say, what happens to the land speed because of the Earth's rotation as you move away from the equator? It slows down. But that airspeed is going to stay the same. So you have these jet streams that are going to go toward the east because of the air in the upper atmosphere going at the equator speed and the land down below going at a slower speed. So you have the jet streams that are up high that are going like this. And so when we flew to Hong Kong, we were going against that jet stream, so it took longer to get there. Coming back from Hong Kong, we were going with it. It took less time. So all of these effects, they're all explained by physics, and the Coriolis effect is part of that. Now, you guys have seen cyclonic storms. Cyclonic storms have their direction of rotation caused by this Coriolis effect. If you have a low pressure system, stuff coming into it is going to deviate like that, and it makes it rotate, giving you the cyclonic storms as shown in the second picture, C. Now, some people say, aha, and the toilet. You guys may have seen the whole Simpsons episode where Bart makes a collect call to Australia to ask them which way the toilet drains. No? Okay, it's Simpsons, so it's kind of funny. And in the end, it causes an international incident because he racks up, like a $1,000 phone bill for the poor kid who answered his collect call to ask him what direction the toilet rotates. And to settle the international incident, they go down to Australia to apologize. And so Bart's all excited because he's going to be able to finish his scientific inquiry and see what direction the toilet rotates. And he goes to the bathroom in the U.S. Embassy. And they have this big mechanism to make sure that it rotates the same direction they rotate here in the Northern Hemisphere. Okay, if you want to actually know the truth about this, the Coriolis effect, if you go closer to the center of the Earth, you're going to have a slower rotational speed, and so it does make a difference, right? Really, really tiny for something the size of a toilet. So if you just did an experiment with a non-biased toilet, you would be very close to 50-50 on the direction that it rotated. But our toilets are made so that the water comes out at an angle so that they will rotate always the same direction and effectively, because it drains much better when the water is rotating than if it's still just trying to drop. So they put them in to make sure it will rotate. And so that's what makes your toilet water spiral the way it does. If we had super big toilets, then we could come to the Coriolis effect and it would have a significant effect. Any questions about the Coriolis effect then? Because we do have a clicker question coming up as soon as you say no. All right, I'm going with no questions. So going to our clicker question, it is, wow, Paris, that was super fast. He had the question in before, well, I guess, yeah. Why do we observe the Coriolis effect if Coriolis force is fictitious? Joel. The channel is 33. And the session ID is WebPhys. Okay, give it just 5 more seconds. All right, stop it now. Just before I hit stop, it was 6, 6, 32, and 6. So one person changed and one person answered. We have a pretty good consensus here, so let's just go straight to James Clegg, giving us his reasoning behind his answer. So what's your answer and what's your reasoning?
So, because I chose C.
Okay, he chose C.
So, since the Earth is rotating, but the winds are not necessarily going the same speed, C would be going the other direction.
Okay, so he said because the Earth is rotating and the speed of the surface of the Earth changes with radius from the axis of rotation. I'm adding that for you. Whereas the air is not connected, so the air is just going to maintain its rotational velocity. The air is at a different rotational speed than the Earth, and thus it appears that it's being pushed. But in fact, it's not being pushed. It's once again, just like with the, quote, centrifugal force that's fictitious, it's just inertia in action. Okay, good answer. And now we're going to move to energy. So this picture, I believe it comes from our textbook. I find it interesting that it says it's a photograph from Iowa taken by somebody whose name is Jürgen, who lives in Germany. But energy is a really important thing in our lives. We talk about things like, energy shortage or using green energy and that kind of thing. So it's important that we have some understanding of what energy is really talking about. And so I have a question here. How many forms of energy can you see? This, of course, presupposes you know something about energy. If you don't know anything about energy, your answer would be, I don't see any yet. You haven't taught me yet. So just throwing it out there, what forms of energy can you see in this picture?
Solar.
Okay, solar energy. Somebody over at Southwestern want to throw an answer out there? I think somebody might be answering, but I can't hear anything clearly.
Wind energy.
Okay, wind energy. Wind energy. How about somebody here? You see another form of energy? Okay, somebody said nuclear. The sun energy, the sun's source of energy is nuclear, so I'll put that there with the sun. Got an answer, Cody? Okay, Cody says potential energy. Now, potential energy is a class of energy, and there are many different types of potential energy. Do you have a specific one in mind?
Gravitational.
Okay, gravitational. I'm going to stop asking people questions now because you could go for a long time, especially if you want to get nitty gritty. You also have things like, for instance, chemical potential energy. If those wind turbines are moving, you have kinetic energy. I can't tell if they're moving or not, but I'm just going to assume they are because of the wind. We're going to have what we call thermal energy because clearly it's going to be not absolute zero there. There's a lot of different forms of energy. And so we're going to learn initially about mechanical energy. Mechanical energy is energy that we can use efficiently, basically. So we'll learn more about that mechanical energy as we go through the lecture today. So starting off, we will work with work. Now, you guys have homework. That's work, right? I have work. I'm doing it right now. I'm working hard because I'm talking, right? Mechanical work is a very clearly defined thing. When we talk about, I'm going to work, it's fairly nebulous and it's just, you're doing something. But mechanical work has to have two pieces. You have to have a force and you have to have motion. And it's not just motion that is parallel to the force. The equation for mechanical work is shown just below. Work is equal to force vector, so it has direction, dot, yes, we just say dot for that, and then the change in position, another vector. Now, most everybody here, I think it's a prerequisite, you've taken algebra. And in algebra, at least in theory, you learn about dot products, which are also called scalar products or inner products. The dot product is the multiplication of just the parallel parts of two vectors. I can't multiply, I can't say force vector times distance vector. That is a nonsensical statement because they have direction. I can't multiply directions. So the dot product is a way to do a multiplication involving vectors and is multiplying the parallel parts. So if I have a vector that goes like this, let's say my force vector is like this, and the distance vector is like this, I should call it delta x because that's what it's called up above. If I want to multiply the parallel parts, I need to find the angle between the two vectors. And so if I name that angle theta, then I could either find the component of force parallel to the x, to the motion, or the component of the motion that's parallel to the force. So let's start this easy. Let's find the component of force that is parallel to the motion. So I have that force vector. How do I find the component that's parallel to my x direction? Okay, it's the adjacent side. And so the adjacent side is going to be the magnitude of the force times cosine of the angle between the two. Now, if I had gone the other way, if I'd said, let's find the component of x that's parallel to the force, I would have had the component of delta x parallel to the force was the magnitude of delta x cosine of theta. So I would have gotten the same answer both ways. So this here is the result of a dot product. It's also called a scalar product because it's no longer a vector. It's just a magnitude with units, of course. So force magnitude times delta x magnitude times cosine theta. Now, just to make sure we understand the importance of vector signs, what makes this a magnitude and this a vector? It's simply having that on top. So if I put a vector sign here, this would have been wrong. This needs to not have a vector sign, but I needed to have a vector sign in the original equation where it shows the dot product. So when you get these dot products, when you see them, it's nothing to freak out about. You can just say, the dot product means I'm going to take the magnitude of one times the magnitude of the other times the cosine of the angle between the two. So you have to find that angle between them. So now if we look at this picture, Up at the top, the dude's pushing the lawnmower, something I'm going to be doing after 3 today. So as he's pushing the lawnmower, you got a question, Jonathan?
Sorry, just on the dot product. So, is there a way to denote which vector it's going to be parallel to? Like, only
It does not matter.
it doesn't
Because
matter.
it's a scalar outcome and you only care about the angle between the two, then it doesn't matter.
Right. But depending on which one you treat as the x direction, you could
Mhm.
end up technically having it be secant theta instead of cosine theta if you put a 90-degree angle in a different place.
Okay, so I'm guessing the people in Southwest didn't hear that. He's saying that if we had done it the other way, then I would have had secant instead of cosine. If I had done it the other direction, if I tried to find, so this was F component, parallel to delta x. If I had done it the other way, if I wanted to find the delta x component parallel to F, I have the same angle between the two, but now I would have my coordinate system is like this. Here's my direction for F, so I'll put F hat there to say it's my direction for F. And so I need my component directions to be like this and like, well, and like this. And so I would have, this is my right angle for that comparison. And my hypotenuse would be delta x still. And my adjacent side would be the delta x parallel to F. And so adjacent hypotenuse, it would still be cosine to find. Okay, it's good to get those questions out. My whole way of going through school when I was in college, I was a bad student. I didn't read the textbook before. That's part of the reason I do the concept coach, to make sure you're better than me. But when the teacher was teaching, if I didn't understand, I'd ask a question. So when I got to the homework, I would be able to do it and not be like, I didn't understand that in class. So in this first case, the lawnmower, the direction of the force he's putting on the lawnmower is downward at an angle. And so the simple question is he doing work on the lawnmower? He's moving the lawnmower forward, but his force is pushing down and forward. Is it doing work on the lawnmower? I have people saying, which is yes. So Keela, since you're the closest person, why is how can you justify that he is doing work on the lawnmower there?
We said that work needed force and motion parallel.
Mm-hmm.
So there's force and motion parallel there.
Okay, well, the force is not parallel to the motion, but there is a component of the force that's parallel to the motion. So that means a component of the force is doing work. A component of the force, the part that's perpendicular to the motion, is doing no work. So now if we look at picture B, gentleman there holding his briefcase, he's standing still. Is there work being done on the briefcase? No, there is not. Why not? No motion. Okay, what about picture C? He's got the briefcase and he's walking at a constant speed. Is he doing work on the briefcase there? I had mixed answers. So let's just, instead of putting somebody on the spot, let's just go through it. Is there a force in picture C? Yes. Is there motion in picture C? Yes. Is that motion parallel to the force? No. So since there's no motion parallel to the force, there's no work done. I'll leave the last two for the clicker question that's coming up right after this. Just another statement before we go to the clicker question. I have this mass here. I put it on the table. Is the table doing any work on that mass? No. Now I put it on my hand. I'm going to hold it as stationary as I can. Actually, let me move over here maybe. Is my hand doing any work on it if it's just stationary there? No. Am I expending energy to hold it there? I am. Was the table expending energy to hold it stationary on the table? No, it wasn't. table doesn't have some method of giving it energy. So the table wasn't explaining energy, I was. That was the key for one of the concept coach questions. The one about Carlos climbing up the hill, or hiking up the hill probably, more likely. And he had to choose between the zigzag path or the direct route. I like to relate this to, if you're at Yosemite and you want to go from the valley floor up to Glacier Point, you can take the 4-mile trail, which is actually 5 miles long. It's one of those oddities where the trail was altered since they first made it and now it's longer. Or you can take the Panorama Trail. Panorama Trail is really beautiful. I don't know. How many people here have taken that hike? Cody. All right. My dad and I did it when I was 7. Then we did it again when I was 37. It was easier when I was 7. And 2 days after I got married, I took my wife on it because I thought it was such a wonderful hike. Anyway, the Panorama Trail is like 10 miles. So if you look at that, which one's going to be more work? In terms of mechanical work, we'll learn that it's the same amount of mechanical energy you have to use both ways. But when you're walking, you have to exert energy to start your motion. And then you have to use energy to stop your motion with your steps. So each step takes energy to start and to stop. And so even if you're walking on level ground, you can get tired. You watch Olympic sprinters, they're running on level ground, but they are getting tired. They're using a lot of energy. And so it turns out the longer path, if you have the same change in mechanical energy, that is the same change in elevation, the one that's the longer path is going to require more energy because our bodies they require energy even when we're not doing a work with that energy per se. Okay, so let's go to that clicker question, and you can answer starting now, Paris. He's holding off. Okay, now this has multiple answers. Select all that are correct and then do enter. Then hit enter. You can't do it. It's not an action. Hitting is the action. Okay, I'll give it about 2 more minutes. 2 more minutes? What am I saying? I'm at seconds there. I'm stopping now. That was very genius of me. Okay, so the answers we got here. Where did I put the stylus?
Over there.
Yeah, thanks. It's good to have a memory that's more than a few seconds long. So the answers we had were 36, 6, 10, 35, and 20. Now what I'm going to do is I'm going to call, hopefully these are nice and shuffled, I'm going to call a student to answer each one. And the first lucky student is at Southwestern, and that is Crystal Granados. Tell us if A was yes or no, and give your reasoning why. Okay, I put yes because what was the reason? Let me turn the volume up some more. Okay, try once more because we really didn't hear your answer. Yes, because?
It was being done to the mower. There was work being done to the mower.
Well, the question is why? Why would there be work being done to the mower?
Because it's moving direction.
Okay, because it's moving and it has force and the motion is at least partially parallel. Okay, thanks. I don't know your name, but the guy who's helping so we can hear. That is very beneficial to us. Okay, for part B, Randy, what'd you answer and why?
No, because he's not moving at all, so there's no motion.
Okay, yes. No, because no motion. Okay. Third will be Sandy Shirkova. C.
No, because
Because what?
There's no parallel function.
Okay. Because motion is not parallel to force. All right. Next up is not here. Carrie. Carrie Havman, in case there's a Carrie over there.
I said yes, because there is a component of the force that is parallel to the directions.
Okay, those two parallel lines mean parallel. That's absolutely right. And last of all, Antonio Rodriguez, which is a Southwestern student.
I only answered one, and that was A.
Okay, so you said no for E?
No. Well, I didn't answer. I didn't put E.
So
Yeah.
Number 8.
yes. So what you're saying is for E you said there was no work, correct?
Yeah.
And so what was your reason for saying that there was no work in E?
It's not parallel to the force.
It is parallel to force. Okay. So the correct answer, E, was yes, because it is parallel to the force. You had the force of tension there. I see Manuel must have got that one right. The force of tension was upward. The distance was downward. Now, this one was a little trickier. As you can see by the numbers, people didn't get this one as readily as they did the others. What was tricky about it? They were in opposite directions. They're anti-parallel. And in the case of opposite directions, your force is one direction, your distance is negative in that direction, so you have a negative work. So in lowering this briefcase, it did a negative work, the lift did. Now gravity, on the other hand, if we looked at gravity, what direction is the force of gravity? Down. Was there motion downward? Yeah. So gravity did a positive work on it as it went down, and the tension did a negative work. And so we will, on the next slide, bring more out about that. But we have to take a little interlude because graphs, we love them in physics because they tell us so much. And if you have a graph with force versus distance, it will tell you how much work had to be done. Because that equation of force parallel, so in these pictures, you'll see it says force cosine theta to say it's the force parallel to the motion. And distance, if I have a curve, the first one just shows a straight line. If I have force in the vertical axis, distance in the horizontal, and I'm doing the force parallel times the distance, I can do that on the graph, and I find that it's the equation that gives me the area that's underneath the line. And if I have a force that's changing, I can actually say, well, with the same principle, let's make a really tiny piece, small width d sub I, and multiply it by the force for that distance, then go to another small distance with a slightly different force, and we multiply them up. Each one of those little force times distance gives me the work for that distance, and you add them all together, and you again have the entire area under the curve. So the bottom line here is the work done by a force can be calculated graphically by just doing the area under a force parallel to the distance versus distance graph. So an experiment that we used to do, it wasn't as good the way they did it before I arrived at PUC. They used to do it with guns. They would fire a .22 bullet into a block of wood and determine how fast the bullet was going before it hit the wood. They did that until a student missed, and the bullet ricocheted across the classroom Fortunately, hit nobody, but they decide guns not safe in the classroom. We physicists are smart that way. Okay, so then they went to a bow and arrow, which was great because with the bow and arrow, of course, you have to draw the arrow back on that bow. And so we would actually make a graph, and you'd put 1 kilogram and measure how far back the string moved. Put another kilogram, measure how far back the string moved. And then, of course, mass times g is the force that you had hanging from it. And you could make a graph that showed the distance on this axis and the force that you applied on this axis. In that case, we were using centimeters. And you had something that went like this. And then the students could add up the area underneath to find the work that had been done in drawing back the bow. So it was very useful. And then you release it, and in theory, the bow is going to return all that energy, which is, well, I guess there's one more slide. I thought it was on the next slide. This is a simple example of something moving on a roller, putting all the forces present. So now, no clicker question involved here, just throwing it out there. Are there any forces that are going to do work? Notice it's moving to the right. You've got 4 forces. Any forces that are going to do work?
Yes.
Yes. Two we have. What are the 2 that you chose?
The force applied and the force of friction.
That's right. Now, the force of friction is just labeled with the lowercase f, but he's right. That's the force of friction. And those are the 2 that are going to do work because they're parallel to the distance. Which one's going to do positive work?
Force applied.
The force applied. And so then we'll just calculate the work applied is equal to force applied times the distance. Notice I didn't put any vector signs or a cosine of an angle. Why didn't I put either one? It's mostly because I'm lazy, but there's a good reason to do it. Cosine of, in this case, 0 degrees. Cosine of 0 degrees is 1. And since I know cosine of 0 degrees is 1, I just left it off. If you're not confident that way, you can go ahead and put times cosine of 0 degrees just to make sure. By the way, make sure that you have your calculator in the right units. I've already had 2 tests where the calculator was in radians and the test question was in degrees. And yes, I see one of the students talking about, yes, I did that. You figured it out. So then I just do my calculation here. 120 newtons times 0.800 meters. Assume we have 3 significant digits in that newtons. And 8 times 12 is... trying to go back to, 3rd grade when we learned that. 96.0. I have 3 significant digits. What do I have for my units here? Just reading directly. Okay, just reading directly. Newtons times meters. And so the Newton times meter, we give a new unit that's just a Newton times a meter, a joule. Now remember, a Newton itself is a kilogram times a meter per second squared. So that means a joule is a kilogram times a meter squared per second squared. So the joule and the Newton are both derived units based on kilograms, meters, and seconds. You might remember from the very beginning when we talked about units, I said virtually everything we're doing is going to be just those 3 units. So we get to temperature. So the joule, it's James Prescott Joule or something like that. It's named after him. And so that's the unit we use for energy. I always put it newtons times meters, never, ever like this. What's wrong with putting it that way? It reads the same as a millinewton, and you want your unit to be distinct, not ambiguous. So if it says mn, it's going to be millinewton. If it says nm, then it'll be joules, newtons times meters. Okay, so we calculated the work done by the force applied, doing the same thing for the force of friction. And I'll go ahead and put cosine of 180 degrees here. Being explicit, cosine of 180 degrees is -1. So that's 5.00 newtons times 0.800 meters times -1 is equal to minus 4.00 joules. So the net work done here is the sum of the two works. The work done by the force applied and the force of friction. So the work net is equal to 96.0 newtons times meters plus a negative 4.00 joules. Let me change that to joules. And so there we have the net work that was done on the package. This stuff here is not super complicated. So let's get more complicated. Why not, right? Talk about potential energy. Potential energy is energy something has because of its position or configuration. So the standard example for potential energy is gravitational potential energy. If I have something up here, gravity has the potential to do work. If I stop putting my hand on it, if I let go, gravity did work to make it come down. It did work because the force of gravity was down and the motion was down. So gravity gives us a potential energy. It's not the only potential energy, but it's the only one we're going to talk about today. So if we look at that gravitational potential energy, we have an object here. Force of gravity is equal to mg. And so if it falls a distance h, then the work done is the force parallel, which times the h. And so my work is, mgh. Now in this case, the force, if it falls down, that's a positive work done by gravity, right? Gravity is what we call a conservative force. It's conservative because it will give back energy. If you do work against gravity, for instance, if I take this mass and I do work and I raise it, gravity will return that energy back and make it come back down. It doesn't take some of it and give some back, it gives it all back. And so for forces that are like that, forces that we call conservative forces, we define a potential energy, and the potential energy is actually defined by its change. That is, the change in potential energy is minus the work conservative, or here I put work conservative is minus the change in potential energy. So it turns out that potential energy for gravity is equal to mgh, and when it went down, the work was minus the final potential energy minus initial. And of course, notice I have a minus parentheses something minus. So it's going to turn out to be positive mgh initial minus mgh final. And so in the case of the falling mass, the work done by gravity is going to be mg times the height initial minus mg height final. Now we have an important decision you always get to make in a problem. I just had height initial and height final in that calculation. So you choose, where do I want to make my reference for height? And you can choose obvious places or silly places. I could say, okay, I'm going to choose the moon for my reference for height, and it was this far from the moon and this far from the moon. Right? That's silly because that's going to require a lot more work. Or I could simply say, I'm going to say that where it ended was a height of 0. I've used that as my reference point. And where it started was a height h, and then it's very trivial to do the work. So when you're working with gravitational force, you need to decide, unless the problem tells you already, where you're going to use your reference for height. The gravitational potential energy doesn't care where you set that reference as long as you're using this form. When we get to universal gravitation for it, well, then it does care. Okay. I think I'm a funny man, of course. Why else would I go into physics? What kind of forces have an associated potential energy? Okay, few people are humoring me and chuckling. Thank you. Appreciate that. Okay, I'm just going to give another 5 seconds and we'll cut it off. Okay, so we had 25, 3, geez, 18 and 1. Getting ahead of myself, I changed it. Okay, I would like you to discuss with the person next to you for just a minute your answer, their answer, and try to help each other come to a better understanding.
Holding your fist into it, and it has some energy that's going to get back. It's not going to get back all the way.
Okay, I'm going to now re-poll it for everybody, and then it's going to be Brady who gets to explain his answer. So everybody answer a second time. Answer the same question a second time. Okay, cutting it off here. So we had the second time around a big shift. All right, Brady, what answer did you choose and why?
I did C.
Okay, Brady chose C.
Because potential energy is based on something returning to a natural state, and conservative forces define something that is going to give back all the energy that was put into it.
Okay, and that's exactly right. You have to have the force give back everything that was put into it, which we call a conservative force, if you're going to define potential energy. What's an example of a force that's not conservative, that's not going to have potential energy associated with it? How about friction? Friction does not return energy. If I take the mass and I slide it on the table, it just stops. The friction is not going to make it move again. Now, I've got a demonstration of 2 problems, and we're not going to get there. Jonathan.
What about something that returns some of the energy back, like the force of tension or something, like if you're pushing on it, or elasticity or something?
Well, elasticity is conservative because it'll give it all back. Okay. If you have plasticity, then it's non-conservative. Right? Plasticity is when you have the permanent deformation. Okay, kinetic energy. Kinetic energy is energy in motion. And so we have here just a simple example of a roller coaster going down a track. A basic definition for work, for energy is the ability to do work. So we studied work, a force, times distance parallel, something that can do work. is going to be able to, move things and such. Kinetic energy is energy something has, the ability to do work something has because of motion, that kinetic. And it has the equation of kinetic energy is 1/2 mass times speed squared. So if something is going faster, it will have a higher speed and thus a higher kinetic energy. Slower, lower speed, lower kinetic energy. Now, because of time, I'll have to stop here, so I will do my demonstration with the swinging bowling ball and everything next class period. I might have to go change the homework because I made it beforehand being confident I was going to get through the next slide. So have a great weekend. Hope you're enjoying your first full day of fall.